In this video, I'm just recording basically some extra content for the Linear Algebra 2 course that I'm TAing this spring 2020. And this video, I'm going to talk about linear independence, linear dependence, and I'm going to go through an example of finding a basis. Now, anyone who's in my section for this course has already heard me drill on about definitions. And I'm not going to stop because they really are the #1 most important thing to have down in this course. Of course, you need to have an understanding of things. You need to have some sort of idea of how typical proofs go, maybe know some important proofs, some key ideas. All these things are important, sure. But as I've told people before, if you don't know the definitions, you can't even get off the ground, right? Like if there's some major theorem and you forget the proof, fine. Maybe you can come up with it again. Maybe you can remember it or reinvent it or come up with a new one during the exam. But if you don't know the definition of say, linear dependence, and you're supposed to prove some result about linear dependence, then how can you even possibly try to start the question if you don't have the definition of the thing you're trying to prove, right? And when I say this, I want to be clear that it's important to have the precise definition. I'm talking verbatim, symbol for symbol, exactly in its place. I highly recommend looking at the suggested textbook for this course and copying the definition out exactly many times over until it's buried in your head. Okay, forget that extra note. That's from something else. So on that note, I want to talk about first the notion of linear independence, right? This is probably one of the most important, debatably most important definitions in this entire course. So linear independence, right? The idea is that this says that all the vectors are independent in some set of each other. So none of them can be written as a linear combination, hence linear independence of the other, right? So we say that a set V1 up to Vn of vectors. So notice this is not the span, right? This is a finite set. There's just n vectors in this finite set. So a set of vectors belonging to a vector space big V is said to be linearly independent if and so now the condition is if C1 V1 plus C2 V2 plus ... up to Cn Vn equals the 0 vector, implies that each of these coefficients are equal to 0. So it's really important to have the direction of this correctly, right? Of course, we can always find, right? If you have any vectors, they don't even need to be linearly independent, right? If you have any vectors, and if you always choose you can always choose the coefficients to be 0. And of course, you multiply any vector by 0, you get the 0 vector. You add the 0 vector a bunch of times, you get the 0 vector. So yes, it's always true that you can pick C1 up to Cn to all be equal to 0. For any vectors, if you take those to be the coefficients, you'll end up with the 0 vector, right? But what this statement is saying here is that this is the only way you can get the 0 vector here, right? So it says if you have some linear combination such that that linear combination is equal to the zero vector. This is only possible. It forces you to conclude that these coefficients are all equal to zero. And I want to highlight something, the important notion of linear independence, linear dependence, because it's also going to give us practice in finding the appropriate negation of the statement, right? So a set of vectors, which is linearly dependent, well, of course, this is just a set of vectors that is not linearly independent, right? So what would that mean? Well, a set of vectors v1 up to vn, just going to take a moment to write this out. Of course, I write L dot D as a shorthand for linearly dependent. So what does this mean? If this statement says essentially that the only linear combination of these vectors resulting in the zero vector is to take each of the coefficients equal to zero, then the negation of that statement means that there is some linear combination such that not all of them are zero, and that linear combination is the zero vector. So here's the important part. When we're negating this part, it doesn't mean that each of these coefficients are non-zero. It just means that at least one of them is non-zero. That's an important difference, right? So a linearly dependent set, so this set is said to be linearly dependent if there exists real numbers C1 up to Cn in the real numbers, which are not all zero. So again, this doesn't mean that each of these are non-zero. It just means that not all of them, right? There's at least one of these that are not zero. Such that the linear combination, right, C1 times V1 up to Cn times Vn is equal to the zero vector. Right, so linear independence says that the only way to add scalar multiples of the set together and to end up in the zero vector is if all those scalar multiples are themselves zero. Linear dependence says that there is some way to take numbers that are not all zero, add together the scalar multiples of these vectors, and get the zero vector. Okay, so I just wanted to really highlight the difference between those. And in fact, to save people's attention span, I think I'll put the example I was going to do in another video. So thanks for watching, and study hard.